Okay. Hello, everybody. Today we're going to be going over the Organic Chemistry 2 Exam 1 for spring of 2022. Unfortunately, the recording that I had made on Monday did not record correctly, so I'm going to be re-recording this and uploading this tonight, the night of the 14th, which is Valentine's Day. Wow. Okay. Um, so to begin, we're going to start with the nomenclature section. So, the first thing to do with the first nomenclature is that we have an epoxide. So, there are two ways to name this. Technically, the correct way is that the OH group is the parent chain, but I'm also going to be naming it as if the epoxide was the parent chain. So, the first one I'm going to do is the alcohol parent chain. So, the alcohol parent chain, we want the longest chain of carbons first, starting with the alcohol. So we're going to start numbering from 1, 2, 3, and 4. So now that we have this numbered, we can give the parent name. So the parent chain is going to be 4 carbons long, so butane, but it's going to be an alcohol, and so that would call it, it'd be an alcohol on carbon 1 specifically. So we're going to call it 1-butanol. And then for this, as for substituents, subs, we know on carbon 4 we have bromine, so we're going to put 4-bromo. And we have to label this epoxide ring as a substituent as well. So to do that, we're going to be referring to this as 2,3 epoxy. EPOXY, right? And then lastly, to do stereochemistry, we see that we have 2 hydrogens here, and these are both the same groups. So because of that, we don't actually have to do RNS configuration. We can actually just call this cis. But if we were going to do RNS, then we would still be allowed to. If you wanted to do RNS, you would look at carbons 2 and carbon 3 because they are both the carbons that have the 4 groups on them. So 2, 3, 4. Okay, so carbon 2 is connected to a carbon right here, a hydrogen. So where the hydrogen is going to be group 4. It's connected to an oxygen this way. It's connected to another carbon this way. So between the wedge and the bottom of the oxirane, it has, or the epoxide, it has two carbons. So obviously the oxygen is going to be labeled as the biggest group. So we're going to put 1 for the oxygen. And then for across this bottom side, we have a carbon that's attached to an oxygen, a hydrogen, and another carbon. And this carbon right here is attached to 2 hydrogens and an oxygen. So oxygen and 2 hydrogens. So because this one is attached to an oxygen, a hydrogen, and a carbon, this is going to be carbon number 3 is going to be our number 2. And then this last one is going to be our number 3. So if we were to do the arrows, this would be a clockwise arrow. So our stereochemistry would begin to R. Sorry, not S. I don't know why I wrote that. To R for clockwise. And as for the other side, I'm going to choose a different color. As for the other side, we have carbon 3, which is connected to a carbon with 2 hydrogens and a bromine, an oxygen, which is going to be 1, the hydrogen, which is going to be 4, and another carbon going this way that is attached to an oxygen, a carbon, and a hydrogen. So from this, we have the oxygen, the carbon with the oxygen, carbon, and hydrogen is going to be labeled as number 2. And then the carbon with 2 hydrogens and the bromine is going to be number 3. So whenever we do an arrow this way, this is going to be 3s, considered because it's called counterclockwise. So 2r, comma 3s. So to put it all together, now we can put the cis, or 2r comma 3s dash, we're going to start with bromo and then epoxy. So 4 dash bromo dash 2 comma 3 dash epoxy dash 1 dash butanol. And one thing you can also put is epoxy butan dash 1 dash OL. And lastly, I'm going to be showing you guys the epoxide naming. So I'm going to redraw this actually, so just so that I have like a clear thing. I don't want to erase everything I've done. BRH, it is an OH off of this, and another H. So whenever we label the epoxide as the parent chain, we're going to start with labeling the oxygen as number 1, and then these are going to be either 2 or 3. So they can be either 2 or 3, and we're going to find out how we can determine that. So for the parent chain, whenever we label the epoxide as the parent, is going to be called the epoxy, or oxirane, sorry, not epoxy. It's going to be called an oxirane. So, and then now we can, for subs, we know we have the, this 4-bromo is no longer we call that. So these are now going to be 2 different complex subs. So in this one, we have a 1 carbon chain with a bromine on it. So our first sub is going to be a 1 dash bromo. I'm not putting the actual carbons and the labeling carbons yet. This is just the parentheses name. 1 dash bromo methyl. And then another sub is going to be the 1 dash hydroxymethyl. And then lastly, what we're going to want to do is to get the stereochemistry. Excuse me 1 second. Okay, for the stereochemistry, we can do the same thing. We can call this 2R3S or cis. So I'm going to choose to call it cis for simplicity's sake. So now that we have that, we can finally name the compound. Well, not now, but we would have to first figure out the B and H. So because B comes before H, this is going to be a 2, and this is going to be a 3. And then finally we can put it all together. So we have a cis dash 2 bromomethyl. So because these are on carbon 1s, we don't actually have to put these in parentheses. I just did that for, I don't know, good practice. That's just something I do, I suppose. 2 dash bromo methyl dash 3 dash hydroxymethyl oxirane. And moving on, in this structure we have an ether. Remember for ethers that they actually don't have priority over other over alkenes. So while it may be uh, like maybe tempting to like start from like 1 2 right here, just remember that it's not gonna be like an alcohol. It's gonna be a little bit different. So these ethers don't have the same priority as alcohols do. They actually have a similar priority to, I believe, halides. They're a little bit on the lower end, so we're going to be considering the alkene as the priority group. So whenever we start with alkenes, we have to make sure that we have as many alkenes in the chain as possible and not just the longest chain. So we want the longest chain of alkenes with the most number of alkenes possible. So if that is a three chain, a chain of three alkenes that's 4 carbons long is going to be more important. So if we have a chain of alkenes that is, let's say like this, that is 1 2 3 4 5 6. So this is a 6 carbon long chain of alkenes. And then we have one that's going, let's just say like we have like 15 carbons this way. And then we just have an extra alkene right here. So even if this one had like as many carbons as it had, and it, let's say it had one extra, right? So if we went from this way up, we would only get 4 alkenes. So even though it'd be like a 12 carbon chain, this alkene this way with 5 alkenes but less carbons is actually going to be more beneficial, or is going to be more, it's going to be a higher priority. So this is going to be our parent chain, this one. So to expand on that, now whenever we do this, we have to make sure that we do the same thing. So we're going to start by numbering 1 2 3 4 5 6 and 7, and always make sure that you number backwards and forwards. 1 2 3 4 5 6 and 7. So we see that our double bonds are both on both the blue and red numbering are on 1 and 6. So that means we have to go to subs to break the tie. So with the red numbering, we have our subs on 3 and 4. And with the blue numbering, we have our substituents on number 4 and 5. So because of that, we're going to be going with the red numbering. So in order to start naming, let's erase the blue numbering. And let's start. So our first goal is to name the parent. So parent would be a 1,6 dash hepta. And remember, because we have 2 alkenes, we're going to start with the prefix di-ene. So we have a 1,6 heptadiene. And then as for subs, we can begin by naming the sub on carbon 3. So whenever we have an ether as a sub, an ether as a sub, then we're going to be referring to it by the chain that it is, and then putting oxy at the end. So in this case, we have an ethyl group on this. So we're going to start with 3-ethyl. And instead of putting ethyl oxy, what we're actually going to do is we're going to erase the YL of ethyl. So, and we're going to replace that with oxy. So it's going to be an ethoxy. Whoa, why did I put a T there? Ethoxy. And as for the sub on carbon 4, we have the 1 2 3 4. This is going to be a butyl group, BUTYL. And lastly, we have to do stereochemistry. So we don't have stereochemistry on any of these alkene bonds because they don't have these alkene bonds both have hydrogens on both ends, meaning that it wouldn't be are identical not identical hydrogens, but they're both these hydrogens are both on the same group, and so that's why we're not able to um, figure out which one is higher or lower. So for that reason, the alkenes are not going to have any stereochemistry, but we are going to have stereochemistry on carbon 3. So to figure out the stereochemistry on carbon 3, what we're going to do is 4, 5, 6, 7. What we're going to do, we're going to label this, and then we're going to go every which way that we can. So we have a hydrogen, 2 carbons, and an oxygen that it's bound to. So hydrogen 4, and then we have 2 carbons here and an oxygen. So the oxygen is going to be number 1. And now whenever we go to this carbon, carbon 2, carbon 2 is bonded twice to a carbon, so C comma C, and it has 1 hydrogen hanging off, so H. And then this carbon, carbon 4, is bound to 2 carbons as well and 1 hydrogen, so C comma C comma H. So because of that, both of these carbons are tied, so we're going to go to the next one. So as for this one, we're going to be going to carbon 1 right here. So this carbon is bound to 2 hydrogens, and for this case, it wouldn't matter which carbon we went to, if we went to this carbon or this carbon, but it's important to stay on the parent chain. So we would go to this carbon, and then now this carbon is attached to 2 hydrogens, and then a carbon, the carbon. So because of that, this is going to take priority on the left group. So this is going to be number 2, and this right group is going to be number 3. So whenever we draw our arrow, we have it going in the clockwise direction. So our stereo, well, for clockwise is R. But remember that we have our smallest group on a wedge and our biggest group on a dash. So our R is going to be flipped to an S. So now finally we have everything that we need to name this chain. So we can start with S, our stereochemistry, dash. We're going to make sure to put the butyl before the ethoxy. So 4 dash butyl dash 3 dash ethoxy. And then the parent to finish it off, dash 1 comma 6 heptadiene. And one thing you can still do, ethoxy hepta dash 1 comma 6 diene. So that is question 2. And then moving on, we have another ether. This time the ether is 4 carbons long on the left side, 4 carbons, and if you just counted from the ether, which is tempting, 1, 2, 3, 4, you would see it's 4 carbons long on this side too, but it's important that we make sure that we have the longest chain, so we would start numbering from this carbon right here, 1, 2, 3, 4, and 5. And so on this side, on the right side, we have a 5 carbon chain, so that's going to take priority over the 4, meaning that this entire ether is going to be a pretty long, I feel like, complex substituent, but we'll see. So we're going to have 2 substituents, 1 substituent on carbon 2 and 1 substituent on carbon 3. If we numbered it backwards, 1, 2, 3, 4, and 5, it would be on 3 and 4. So we're going to be going with the first numbering. Okay. And now what we can do is we can just name the parent chain. So remember that we don't treat ethers much differently as part of the parent. There wouldn't be part of the parent, so this is just going to be a regular pentane. And now to go to subs, We have on carbon 3, we have a methyl group, so 3-methyl. And on carbon 2, we have our ether group. So on the ether group, remember we have to name the chain that the ether is hanging off of, and then put the oxy at the end. So we're gonna start by numbering 1, 2, 3, 4. So we have a 3,3-dichloro. So in the parentheses, we can put the two subs that are on the substituent chain. The 3,3 dichloro, and then to name the chain is going to be butyl, so butyl. But once again, we're going to drop the YL and add the oxy. So but, oxy. And that is all we need, because there's no stereochemistry to be had in this, so we can just put it all together. So we're going to start with the 2-3,3 dichloro butoxy dash 3-methyl pentane. Okay. Moving on, we have ranked the following carbocations in order of increasing stability. So carbocation stability actually goes from tertiary stability is going to be the highest, is greater than secondary stability, and that is greater than primary stability. So whenever we look at this, we're going to make sure that we determine if it's primary, secondary, or tertiary. So on the first one, we have a primary carbon. This carbon is only connected to one carbon right here, so it's a primary. This bond is only connected to two carbons, so we have a secondary carbon, but we do have some resonance right here. So we'll take that into account. And then our third one, we have a tertiary carbocation. This carbon is attached to three carbons. So now what we can do is that we can look at which one is primary. So we have primaries, and we have tertiary, and we have secondary. So we know that the primary is going to be the least stable. So we're going to rank this number 1. And at first glance, we would rank the secondary as second least stable, right? But remember that resonance is a very good stabilizing factor. Stabilizes it a lot. And so because of that, this one with resonance is actually going to be more stable than the tertiary carbocation. So this is going to be number 3, and our tertiary carbocation will be number 2. Moving on, the second one is asking us to put the halides in order of increasing reactivity in sodium iodide and acetone. So this question may look a little bit confusing, but remember sodium iodide and acetone, NaI/acetone. This is a reaction in Argo 1 that might not look familiar to you guys, but it is actually a strong nucleophile with a aprotic solvent, which means this is an SN2 reaction. So one thing to note about SN2 reactions is that they have increasing reaction rate. So its reaction rate increases with a methyl halide, CH3Br, which has the greatest reaction rate, and then primary, and then secondary. So we'll look at it through that lens, and remember that there is no SN2 on sp2 carbons. No SN2 on sp2 at all. That is a rule. So whenever we look at number 2, the first one, we have this bromine on a vinyl position. And if you remember, vinyls are incredibly unreactive. And just to put the nail in the coffin, this carbon that it is on is an sp2 carbon. So it has spp. So it's an sp2 carbon. And we know that sp2 carbons do not undergo SN2. So immediately we can just put that as the least reactive. Now, moving on, we have two secondary halides, and we have to figure out which one is going to be more reactive. So whenever we're doing this, we have to remember that these bromines are not the same. So one of these bromines is 2 away from a double bond, 2 carbons away, and another one is right across, so it's 1 carbon away, and that 1 carbon away position is called the allylic position. So this bromine is secondary allylic. So one thing to note about allylic is that it increases the reaction rate by quite a bit. So because of that, the secondary allylic is gonna have a higher reaction rate than the secondary regular bromine. So this is going to be the most reactive, and this is going to be the middle reaction. Next, number 3, place the following compounds in order of increasing reactivity with methyl MgBr in ether. So this is a Grignard reagent. So one thing to note about Grignard reagents is that they are incredibly basic. So this is basic, and this will come in later in the question. So we have three structures. We have 2 epoxides, epoxide, and an ether. So whenever we have an ether, we know that Grignard reagents do not react with ethers. So immediately this is going to be the least reactive. And now we have to determine which epoxide is going to be more reactive with the Grignard. So one thing that we do need to remember is that it is basic. So that's going to tell us which epoxide is going to react with. So whenever we have a basic solution with an epoxide, we have an acronym that we use called BLAM, BLAM. Whoa, I think my pen is dying. BLAM. That means that basic attacks the least subbed, and acidic attacks the most subbed. So for this one, because we have a Grignard reagent, we're going to be attacking the least subbed. So whenever we have a Grignard reagent, it's going to attack the epoxide from one of these 2 partially positive carbons. So as for the first one, we have 2 carbons that have near identical groups, or that have identical groups. And so because of that, both of these carbons have 2 groups on them. There's not really any preference for the Grignard reagent to attack which one. Whereas whenever we look at this one, we have one of them with only 1 group on them and one of them with 2 groups. So this Grignard reagent is going to have the preference to attack this carbon with only 1 group on it because it's basic. So because of that, we're going to be labeling this one as the most reactive, this one as the second most reactive. And one thing other that you can also think about it like this is that this is gonna have a lot more steric hindrance because this one has the extra methyl group, whereas this one just has a hydrogen attached to it. So it's going to be a little bit easier for the Grignard reagent to come to this less sub side. All right, getting a little bit bored of red, so let's go back to blue. So, okay, on to the next one. Place the following resonance contributors in order of increasing stability. So in this one, we're going to look at all of the charges and see where the charges are going to be the most stable. So in this one, we have the charges on an oxygen, a nitrogen, and a carbon. So first, let's see which ones are going to have a full octet. So whenever we look at an oxygen, we can draw our lone pairs on that. The nitrogen as well, 1, 2, 3, 4. And then our carbon is going to have two lone pairs, or one lone pair, sorry, and a hydrogen attached to it. So now whenever we count, we know the oxygen is going to have a full octet, 1, 2, 3, 4, 5, 6, 7, 8. So 2 in the bond and 6 in the lone pairs. Our nitrogen is going to have 2 bonds and 4 carbons, or 4 electrons in the lone pairs. So it's going to have the total of 8. It fills the octet rule. And our carbon has 3 bonds, sorry, and the electron pair. So it does fill the octet rule. So now we notice that all of them fill the octet rule, and now we have to go by a different way to solve the problem. So we should see that which atoms take the negative charge the best. So if you remember, if we had the periodic table right here, we have a periodic trend of electronegativity, which increases as we go up the group and increases as we go further right down the columns. So now if we look at the periodic table and we compare carbon to nitrogen to oxygen, we see that carbon comes at carbon number 6, nitrogen at number 7, and oxygen at number 8. So if we employ this same method, we know that oxygen is going to be the most electronegative, and carbon is going to be the least electronegative. So from that, we can put it in order of increasing stability. Because we want the most electronegative atom to have the negative charge, we're going to put oxygen at number 3 and carbon at number 1. And lastly, we're going to put nitrogen at number 2. The second part of this question asks us for the hybridization of the carbon atom. So if we were just to look at this carbon atom, just where it's pointed, we would see it has 1, 2, 3, and 4 groups. It looks like a smiley face, nice. So it has 4. So we would consider this an sp3, just off the bat. But we have to make sure that we look at the other resonance contributors. So if we look to the left, we have this one has a hydrogen on it. So it would be 1, 2, and 3. This is an sp2 carbon. And once again, we have another sp2 carbon. So sp2. So both of these carbons are sp2, and this carbon is sp3. So one thing to know is that the hybrid is the one that exists in the real world. So all of these structures, these wouldn't exist. The hybrid is the only one that exists. So because of that, that carbon, although sp3 in this resonance structure, the hybrid moves along like all of these forms, right? The hybrid can move between like all of these just as it exists. So because of that, this sp we know that the hybrid likes to have the lowest energy structure possible. So because of that, we have the sp2 structure, which is going to be our lowest energy. And so our answer for part B will be sp2. Next, place the following compounds in order of increasing reactivity in a Diels-Alder reaction. So in a Diels-Alder reaction, we have a diene and a dienophile. So diene, dienophile. So what happens in the reaction is that one of these bonds is going to attack this bond, and these bonds. This is going to attack this, and it's going to form a cyclohexene ring. So in that case, because this one is going to be the aggressor, let's just say that we have this top bond being the aggressor, right? That means that this top bond is going to be partially negative, correct? So we know that partially negatives attack partially positive bonds. So partially negative, so this must be partially positive. And so because of that, we want, so to have increasing reactivity with the Diels-Alder reaction, we want the diene to be more negative and we want the dienophile to be more positive. So that means for the diene, we want more electron donating groups, and for the dienophile, we want more electron withdrawing groups. Because electron withdrawing groups, if they were like pulled over here, they would withdraw electron density from the alkene double bond, and they would make this partially positive compared to its already partially negative state. So now, whenever we do this, we see that we have dienophiles. So in this case, we want more electron withdrawing groups. So let's take a look. So our first one, we have one electron withdrawing group. This oxygen is going to take some electron density from the double bond, and we have an electron donating group. So the carbons are considered electron donating groups. In this one, we have two carboxyl groups. So we have two electron withdrawing groups, EWG, EWG. And lastly, we have one carboxyl group, and this ether is a electron donating group because it has lone pairs that it can donate to onto this carbon. So because those lone pairs, it is a electron donating group. So now we have labeled all of the groups that we have across our dienophiles, and now we can see which one is the most reactive. So we know we want more electron withdrawing groups for a dienophile. So immediately, this one has one electron withdrawing group, this one has two electron withdrawing groups, and this one only has one. So the one with two electron withdrawing groups is going to be our most reactive. Then we have to consider which one is going to be a better electron donating group, the carbon or the oxygen. So the oxygen has lone pairs to give, right? So the oxygen would be considered a better electron donating group. So because of that, because we don't like electron donating groups in dienophiles, our carbon is going to be the second most reactive, and our ether is going to be our least reactive. Okay. Finally, we're on to the last facts question. This one is asking us about the spectroscopy, about NMR. So let's see. So our first question is asking us for how many signals that they are going to be having. So for that, we're going to be counting all of the unique carbons. So in this case, we have one, and we have another methyl group right here, right beside it. This is also going to be called 1. So both of these methyl groups are considered the same groups. 2, 3, 4, 5, 6, 7, and 8. And remember, for alkenes, because these cannot move around, these are like stuck in place, this hydrogen right here will never be in the spot of this hydrogen. Hydrogen 7 will never be in the spot of hydrogen 8, which means that hydrogen 7 will always be across from a huge group, while hydrogen 6, or hydrogen 8 will only be beside hydrogen 6. So that's why whenever we have just single bonds like CH, the CH, H, bond to an R, all of these hydrogens are the same because this bond can move around. But these these alkene bonds are not able to do that. They're stuck in place. So that is the reason. So we have 8 different signals. So for our first one, we can do signal number 8. Now we want to find the multiplicity of hydrogen A. So on hydrogen A, we want to look at every single hydrogen that's attached to the same, every single carbon that's attached to the carbon that hydrogen A is on. So we're going to look at this carbon and this carbon, as well as this carbon. So we have 3 different carbons to look at. So one of the carbon 3, has 2 hydrogens on it. So we can count that as a 2 plus 1. And then next, we have 2 of the same groups. And to calculate this, we wouldn't have 2 different 3 plus 1s. It would, because they're the same groups, what we're going to instead do is 3 plus 3 plus 1. So because they're the same groups, they're going to go under the same parentheses. And whenever we calculate this out, this is going to be 21. So our multiplicity of HA is going to be 21. Our multiplicity of hydrogen B, which is on carbon 5, this hydrogen is only looking at this carbon, which is bonded to one hydrogen. Because of that, we're just going to do a 1 plus 1, and that gives us the multiplicity of 2. And finally, we have the multiplicity of carbon C. So if we look at carbon C, this carbon is bonded to 3 hydrogens. So whenever we find the multiplicity of a carbon, we are only going to look at the hydrogens that are explicitly attached to that carbon. So now we can just find that, and now we have 3 plus 1, and that is going to be 4. Let me make sure that my mic is unmuted real quick. Give me a second. Yes, it's unmuted. Okay, perfect. Okay. And now we have the multiplicity of carbon C, which is 4. Okay, on to the reaction section. So on the reaction section, we're going to start with this first reaction, Br2H2O. This is a mark addition of OH and Br. So the OH is going to be the mark addition, and the Br is going to go in place of where the least subbed area is. So the first one, we're going to have the OH go onto this bond and the bromine onto this. So what we have is OH and Br like this, in this configuration. Now we have NaOH. This is intramolecular Williamson. And what this does is that whenever we have a structure like this, where the hydroxy group is 1 away from the halide, it is going to form it is going to form an epoxide. So for our next step, we have an epoxide. This, and the bromine leaves. So my battery dying? Okay. Now we have our step, HCl ether. So HCl ether, this is an acid. And what we know about acid is that whenever we have epoxide, they attack the most subside. So now what we can do is that we have the acid attacking this carbon, which breaks off this bond, and then this oxygen is going to become an O minus and attack that hydrogen and become protonated. So now for our third step, our product will look a little bit like this. ClOH, just like that. Right, 1, 2, 3, 4. 1, 2, 3, 4. Okay, perfect. And our last step, we have PCC and CH2Cl2. This forms alcohols into ketones or aldehydes. It's important to remember that PCC only makes ketones and aldehydes, and it is unable to make carboxylic acids. So for our last step, we have our aldehyde, because this is a primary alcohol, so it's going to become an aldehyde. Next, we have two double bonds that can attack this H3O plus, and we have a major and minor. So for this one, we need to figure out which one is going to have the which one is going to be more reactive, this double bond or this double bond. So in order to find out, let's react them with both and see how it turns out. So I'll label this A if this double bond attacks, and I'll label the other one B. So for A, this double bond was to attack the H0 plus. And then we would have a structure that looked like this. So the hydrogen would get bonded here. And I'm choosing the structure like this, even though these are both secondary. Even though these are both secondary positions, I'm choosing the structure like this because either way, we would like some resonance. So if we were to put the positive charge here, it would obviously not have any resonance, and so it wouldn't make sense to put it there. So because we can have resonance with both, then we would try to at least have resonance. We would try to make a product that would have resonance. So we have our structure like this. So this is a secondary with resonance. And then we have our, for if we had B, this carbon attacked this carbon attacked, then we would have a oh, sorry, I miswrote. So the hydrogen would go onto this carbon, and positive charge would go on the tertiary. So this one is going to be tertiary with resonance. And because of that, we know that a tertiary carbocation is more stable. And so even though they both have resonance, the tertiary is going to be the winner. So now what we can do is we can draw this tertiary structure. So we have the tertiary structure, but we do have resonance. So let's draw the resonance contributors. Right. So now we have two different alkenes, and we see that we have a 50 degrees Celsius. So this is going to be in a hot temperature. So in this case, whenever we have hot, we want a more substituted alkene. will be the major product, and if we have cold, it's going to be the less subbed alkene. And usually if you had cold, Dr. Bean would put like 0 degrees Celsius, so there would be like no confusion. So if we had 0 degrees Celsius, we would have the least subbed alkene be the major product, and if we had a more hot, we would have the more subbed alkene. So whenever we look at this, we have 2 subs on this alkene, and we have 3 on this alkene. So because we want more subs, we want this one to be our major product. So on this plus charge, we can put an OH group. So OH, and on this first one, we can put the OH group onto that tertiary carbon for the minor structure. And we are on to the third question. So our first step is HI excess/heat. This is an SN2 like reaction. And remember, SN2 does not react with sp2, so no sp2. So whenever we look at this, we have 2 potential things that we can do. So we know that this ether is a good leaving group. So this is going to be where we react. So we have the choice to either react here or here to cleave one of those bonds. But remember, since we have an SN2-like reaction, what we're going to have is we're going to have an iodine at one of these places. So let's remember that because there's no sp2 on SN2, this iodine will not be able to form here. It's not going to be able to form because this is an sp2 carbon. This carbon is sp2. Right? Whereas this carbon is an sp3 hybridized carbon, spp. So that is an sp3 carbon. So because of that, we're going to be cleaving this bond and leaving this oxygen attached to the benzene ring. So the product from reaction 1 is going to be, we're going to have our benzene ring. The oxygen is going to be protonated from this hydrogen right here that the iodine is attached to. And we're going to have our iodine on carbon 3 of 4. 1, 3, 4. It's going to be on carbon 3. So we have our iodine right there. Next, we have CH3OH and heat. This is an SN1 reaction. So now what we can do with SN1 is that we can just react it with the iodine, and that will replace it with the OCH3 group. So now for step 2, we have our benzene ring, OH, our 4-carbon chain, and now this is going to become an OCH3. Finally, we have NaOH. So this is another intermolecular Williamson, but this one is going to work a little bit differently. So remember prior, we had an intermolecular Williamson where the leaving group was vicinal to the OH. In this case, it is 1, 2, 3, 4, 5, and 6 carbons away. So because of that, intermolecular Williamson does not make ethers. So if we were to make it react over here, it would not create an ether. It would create an ether, and so we can't have that with intermolecular Williamson. So with Williamson, we can only make epoxides. So because of that, what this does instead is that it deprotonates the oxygen. So it's going to become an O-. So our secondary product, the product from the third reaction is going to be an O-, and then the OCH3 is going to stay intact. And lastly, CH3Br, that is just an SN2 reaction. using this as the base, and then CH3Br um, as the recipient, I suppose, or as the halide. Sorry, yeah, the methyl halide. And so our step 4, we're going to have our benzene ring, our O, and then this is going to be having a CH3 on it from the CH3Br, and then our ether. Moving on, we have for our fourth reaction NaNH2 150 and then H plus. This creates a terminal alkene. Alkyne, sorry, not alkene. So we have a terminal alkyne. So what that means is that the alkyne will be on one of these two ends. It wouldn't matter which because they're both the same. But let's draw it out. So our first product is going to be our terminal alkyne. So this is a 5-carbon chain. So we're going to have 5 carbons in this chain as well. 1, 2, 3, 4, 5. So we have a 5-carbon chain. We have a 5-carbon chain right here. And now secondly, HgSO4, H2SO4, H2O. This forms, this creates ketones from alkynes. So it's alkyne to ketone. So remember, ketones have one R group on either side of them. So this is what a ketone looks like. So because of that, we need at least one R group on either side. So we need a carbon on either side. If we were to put the alkyne, for example, or not the alkyne, if we were to put the carboxyl group on this carbon instead, we would have an aldehyde, and this reaction does not make aldehydes. So because of that, we're going to be making it on this carbon. Ooh, wow. We're going to be making it on this carbon right here. So for our second step, we're going to have it on we're going to have the carboxyl group on the second carbon. So carbonyl group, sorry, not carboxyl. So O, 1, 2, 3, 4, 5. So it's on the second carbon, and we have created a ketone. And now finally, this is an acetylide, then H3O plus. This works similar to Grignard in that it attacks the partially positive carbon that the oxygen is attached to, and then breaks the bond off. The oxygen becomes negatively charged and is then protonated by the H3O plus. So the product of this reaction is going to be the same 5 carbons. This oxygen is going to become an alcohol because it was protonated. And now we have our acetylide that is bound to that same carbon. So we have our C, triple bond C dash CH3. Next, we have an ester. This is the structure of an ester. And we have, for our first reaction, a strong reducing agent. So what this reducing agent is going to do is it's going to reduce both of these oxygens and cleave this bond because it is an ester. So whenever we do that, our first, the product from our first reaction is going to cleave this bond and make both of these into alcohols. So it's going to bind an H to them. So next, we're going to have 2 different molecules. Well, not 2 different molecules, I guess. I'm spoiling it. So we have a 1, 2, 3. So 3 carbons and then the OH. for on this side right here. Then on this side we have 3 carbons again, and then an OH. So we have 2 of the same thing. So 2 3-carbon OH. So for this reaction, whenever you are putting the product, it's not necessary for you to put both. You only need to show one. So only one is enough because they are the same thing. And moving forward, we're only going to be using one of these 3-carbon alcohols. So we're only going to be using one of these for step 2. And we're going to continue that throughout the rest of the drawings, I suppose. So next we have a strong oxidizing agent. This is sodium dichromate. So remember, sodium dichromate, when with a primary alcohol, is going to form a carboxylic acid. So compared to if PCC was attached to this, PCC would make this into an aldehyde. Sodium dichromate is going to take it all the way to a carboxylic acid. So what that's going to look like is going to be like this. Finally, we have right here CH3OH/H+. This is, Fischer esterification. So with Fischer esterification, we have an alcohol and a carboxylic acid that form an ester. So we're going to go back to an ester. So our product for step 3 is going to be the same. Wait, 1, 2, 3. So on the 3rd carbon. And then we're going to have our oxygen once again, and then this is going to be bound to a CH3, OCH3. So we have an ester once again. And lastly, for our 4th step, we have Grignard. And so this Grignard is going to be a little bit special. So whenever it attacks this way, this oxygen is going to gain the negative charge. And you might think that it is going to immediately get reprotonated, but that is not the case. This negative charge is actually gonna bounce back because this OCH3 is a good leaving group. So it's gonna bounce back, and then the OCH3 is gonna leave. And then because we have another ketone, so whenever it bounces back, we're gonna have a structure that looks like this. Because we're gonna have another ketone, we're gonna have this attack once again. And this time, whenever it gets the minus charge, it won't be able to attack again. So it will be protonated by the H3O+. So our final product is going to be an alcohol with 2 benzenes on it. So, whoa. OH, and then we can draw our 2 benzene rings. And that will be our final product. And now for our last reaction, we have a Diels-Alder reaction. So in Diels-Alder, what we want is a dienophile that looks like this. So to do that, we're gonna make this axis of symmetry right here, and we're gonna flip these over. So now what we're gonna do, we're just gonna draw this down here. We're gonna have our double bond, we're gonna have our OCH3 and our methyl group right here, CH3. And this is going to be added to a dienophile. Remember, the dienophile is going to attack one of these 2. So in this case, what we're going to do, we're just going to rotate it around so that it's easier to look at. And now finally we can do our reaction. Whenever this reacts right here, what we're gonna have is the cyclohexene. So our product is going to look like this, with a little bit of thinking that will be going into the product. So whenever we make the product, we have to also put our groups on it. So our methyl group is going to be on the top part of um, where the alkene was. So our methyl group can go right here. Then we have our OCH3. This OCH3, whenever we have a diene, we can have two positions. We can have the OCH3 right here, or the OCH3 right here. So this position is called the out position, and this position is called the in position. So whenever we have out, we're going to put the OCH3 on a dash. And whenever we have in, we're going to put the OCH3 on a wedge. So because of that, we're going to put our OCH3 on a dash. So right here, put our OCH3. And now we're almost done, but we do have to figure out where this electron withdrawing group is going to go. So whenever we have an electron withdrawing group, we want it 1, 2 away from the electron donating group. So we have this electron donating group, and we want it 1, 2 away. We want it 1, 2, or 1, 4. So what that means is that whenever we have something, we want it to be on 1 carbon, 2 carbons away, or 1, 2, 3, and 4. So that means that it would either have to be on this carbon or this carbon. So because of that, the only place that the carbonyl group can go is going to be on this bottom carbon right here. So we're going to put our carbonyl right there. And one last thing, because we have to follow the endo rule for Diels-Alder, to show that what we can do is we can put dashes right here, but that just sometimes makes it a little bit more difficult to see. So what we can do instead is just put hydrogens on wedges right here in the middle. So now we have our final product. Moving on to the mechanism. So on this mechanism, we have a cyclohexane that's formed, and then an ether ring. Looks a little bit strange, but we'll see how we can do it. So whenever we have we have this oxygen. This oxygen just seems like it's looking to be protonated. So let's make it attack in a hydrogen of the H3O plus. So now our uh, first drawing is going to be like this. Like this. Now that we have a positive charge, we can make a reaction. So this is a partially negative double bond, and this is a partially positive carbon. So this partially negative double bond can actually attack this carbon, but it can also attack this carbon. So we have two choices. We know that since it's acidic, it's going to attack the more sub side. So it would attack the carbon on the left because that is a more sub side. But another thing that we need to remember is that we are making a cyclohexane, so we need to make the product. So if we look at this, this would create a bond with this carbon right here. So 1, 2, 3, 4, 5, and 6. So that perfectly lines up. So that will be the bond that is created. This this alkene is going to react with that carbon, and then this bond on this oxygen is going to break off. So we have a ring closing reaction. So our next step is going to be just drawing the cyclohexane ring, and we can just number it 1, 2, 3, 4, 5, and 6, and we can put the groups. So 1 has no groups, 2 has a methyl group on it, 3 has no groups, 4 has no groups, 5 has no groups, 6 has a methyl group, and then a here 6 has a methyl group, and then because this bond was cleaved, it has this CH2OH. So we have CH2OH. And now for our charge, carbon 1 lost a bond with carbon 2, but it gained a bond with carbon 6. So carbon 1 is net neutral. Carbon 2 only lost a bond with carbon 1, so carbon 2 is going to be positive. So this is going to be a positive charge. Now what we can do is that we can have this oxygen, the lone pair, attack this positive charge. And what that's going to do is that it's going to form an ether, similar to what we see right here. So if we did that, then we would have our cyclohexane with the methyl group. Actually, I'm going to put the methyl group facing a little bit away. With our methyl group right here, and then our bond to the oxygen that's bonded to the hydrogen, which now has a positive charge because it is bound to two things. And it is bound to carbon 6 right here, which has another methyl group onto it. So we are very close to the final product. Our one last step that we need to do is deprotonate the oxygen. So the way we can do that, H2O, this oxygen really likes that hydrogen, and then the hydrogen breaks its bond with the oxygen, and then we have our final product. So pretty simple mechanism. Our next section, synthesis. So we need to make this using alcohols, alkenes, alkynes of 3 carbons or less. So always remember, just make sure that you read the top. So from this, one thing we can do is cleave off this and have a Grignard reagent MgBr right here. But if you think about it, whenever we go through here, we're gonna have a Br and a vinyl carbon, and it's gonna get really messy from there. So it's not a good idea to do that. So one thing we can do is we can make this into an alkyne. And so the way to do that is that we can use H2 and Lindlar's catalyst. So H2/PD and Lindlar's. So that's also called quinoline. So you can put either of those on your exam, Lindlar's catalyst or quinoline, and they'll both be accepted. Now we have a structure that looks like this. Is that it? So this is the triple bond, and then it has 1, 2, 3, 1, 2. Perfect. Okay. So OH right here. So this is our structure. And now what we can do with this structure is that we can do what we did before. We can cleave that bond, and we can put then H3O plus, and now we'll have our Grignard reagents. So what we can do here is we can call this oxygen, this alcohol is going to become a ketone, and that's going to be bound to an acetylide. So not exactly Grignard, but so the acetylide with the triple bond. So one thing we can do with the acetylide, so to form an acetylide, we need a reaction NaNH2/150, and we have seen this reaction before, but we saw it with hydrogen. And what that does is that it actually protonates the acetylide. So if we didn't put the hydrogen, then it would just be just a acetylide anion. So now what we can do here is just have a regular alkyne. So we have our regular alkyne, and now one thing that the next step that we can do here. Sorry, I'm getting a call. Give me 2 seconds. Okay, so the next thing to do here is to cleave this bond right here, and we can use this as a SN2 reaction. So what we can have now is, oh, arrow's pointing the wrong way. Sorry about that. We can have the CH triple bond CH, or not CH, I suppose. It has to be acetylide. So CH triple bond C minus Na plus. Oh, and also we would have to put Na plus over here too. Na plus, and that is going to be bound to this wrong structure. So it would react with that, and that would be a SN1 reaction, SN2 reaction. And then to get acetylide, remember we just need NaNH2/150, and NaNH2/150 leaves our triple bond CH, and we like alkynes with 3 carbons or less, so that is perfect. And now next, what we can do is we can make this into an alcohol using PCC. This ketone, remember, alcohols can become ketones through PCC. And honestly, you can use PCC, or you can use sodium dichromate, or 207. You can use either of those. You can also use Jones reagent, and that will all create from a secondary alcohol, which is important to note, a secondary alcohol into a ketone. So all of that can be used to form a secondary alcohol into a ketone. These are both very strong, so if you used it with a primary alcohol, it would actually form a carboxylic acid. So make sure only to use that whenever you have a ketone like this, if you want to. Otherwise, just PCC for ketones and aldehydes is just a good idea. So now we have an alcohol of 3 carbons or less, and that's exactly what we like. So we can circle that. That is one of our starting materials. And our last step, this Br. What we can do for this Br, we can just use the reaction PBr3, and that is going to turn that Br into an OH for us. And you know what we can do with OH, Grignard. So then H3O plus, that cleaves it, and now we have a formaldehyde bonded to the Grignard reagent, MgBr. This formaldehyde. For this one, you need to use PCC. If you use Jones or sodium dichromate, this will be counted wrong. So you need to use PCC whenever you have an aldehyde. So now this is just going to become CH3OH, methanol, which is a valid starting material. Now we have MgBr. We can use Mg/ether. That'll add our Mg, so we can now have Br only. And to get that Br off, what we can do this time is PBr3 again. And what that's going to do is make our OH, and now we have a 3-carbon alcohol, which is a valid starting material. And that is our synthesis section. Moving on to spectroscopy. So our first step with spectroscopy is to look at this. So we have C9H12O2. So we have to calculate our unsaturation number. So unsat is going to be calculated by 2C plus 2 minus H plus nitrogens, all divided by 2. So we don't have any nitrogens right now, but in the future you guys will have nitrogens, or you guys probably will have nitrogen, so it's important to remember that nitrogens add to the unsaturation number. So whenever we have this to calculate the unsaturation number, we can just plug everything in. So 18 plus 2 minus 12 all divided by 2. That gives us an unsaturation number of 4. So whenever we have an unsaturation number of 4 or more, remember that that means that we have a benzene ring. So 4 means benzene ring. And now moving to spectroscopy, you see this like very long peak right here. Just around this is going to be our OH stretch. So we have 2 oxygens to take note of, and one of them is going to be an alcohol. So we know, we'll just put what we know right here. So we know it's a benzene. We know we have an alcohol. That's pretty much it so far. So now what we can do is whenever we look at this structure, this is called the doublet structure, and what that means is that we have a para-substituted benzene. So we have a benzene that is substituted at both ends, 1 and 4. And now if we keep moving, we have remnants of the actual exam review. We have 3 hydrogens looking at 3 peaks, which means it is looking at 2 hydrogens. So we have CH3, CH2. This gives us CH3 bonded to CH2, and it's this carbon. And then over here we have 1H. We're going to come back to that. We have 2 H's right here, and this is bound to 1, 2, 3. So this has 4 peaks, so it's bound to 3. So this is going to be a CH2 bound to a CH3, and it is somewhat downfield, so this could be an ether. So let's just say O question mark. And now finally we have CH2, and this CH2 is very downfield as well. So we have a CH2 bound to an oxygen that has, or a carbon, CH2 bound to a carbon. But the thing is, this is so downfield that we would assume that it is actually just an oxygen. So this one is going to be considered an oxygen, and it has no carbons on this side either. So no hydrogens, I mean. So it has nothing on this end. So this side has no hydrogens. Well, this side could have hydrogens actually. It's not ultra pure. So it won't give any signal from this side, but this side for sure, it also won't give any signal. So this CH2 is all alone with no hydrogens adjacent to it on either end. Well, yet. So now we have all of our hints pretty much, more remnants. Now we have all of our hints, so now what we can do is we can start figuring this out. So one last thing that we have right here is we have something slightly downfield, 1H. So we know that we have an alcohol, so this is going to be our OH peak that is looking at, this hydrogen is looking at this oxygen, which is why it has just one peak. So we have our OH. So what we can do to draw this out is that we can just have our benzene ring, and we can start by using what we know. So we know we have a CH2, CH3, and we know that CH2, CH3 is bound to an O because of how downfield it is. So what we can do on one end, we know it has two subs, so we can do OCH2, CH3. And now on the other end, we know we have 9 carbons, 12 hydrogens, 12 hydrogens, and 2 oxygen. So if we count the number of carbons that we've used out of 9, we have 6 in the benzene ring and 2 in this ethoxy group. So that means we only have 1 carbon to play around with. And perfectly, we have 1 carbon right here that doesn't have any bonds on either, that doesn't have any carbons bonded to it, and it has an oxygen bonded to it, which is exactly what we need. So we can put our CH2-OH right here, and that is going to be our final structure. So if we had to not guess and check, but if we had to check our work, then we could look at this CH2. This CH2 is only going to give a signal on this side, and this carbon has no hydrogens. That's exactly what we see, and it's downfield perfectly where this OH is. So that makes sense. Our doublet structure is fine right here. Then we have our CH2 that's bound to CH3. So we have a CH2 bound to a CH3 that is also that is downfield, which is why it's bound to this oxygen right here. So it's an ether. Then moving on, we have our OH peak right here, and it's somewhat downfield. And then we have a CH3, CH2. Usually these are going to come at around 1.2 to like 0.8 ppm. So it being around over here is somewhat like not the best indicator, but it's somewhat of an indicator that it's going to be de-shielded a little bit. So this CH3, CH2 slightly de-shielded. It makes sense that it would be right here. So that would be our final answer for the spectroscopy question. Dang. Because I can't have that circle around it. Just put it off to the side. But yeah, that was our spring 2022 exam review. I wish you guys the best of luck on the test. I know you guys are gonna do great. So yeah, I'm sorry that this came out a little bit late. I'm gonna try to make sure that it doesn't happen again. So yeah, I appreciate you guys, watching the video and everything. So have a good day and good luck on your exam.